All right, I guess we can get started. And it's a pleasure for me to introduce today Melanie Weber. She's a professor in applied mathematics and the computer science in Harvard University. She's also just recently been awarded the Schmidt Fellowship for Early Career. And she today is going to talk about how feature geometry guides modeling design in deep learning. So I'll just leave you the floor.
Yeah. Thanks a lot for the invitation to speak and for the introduction, Kaya. Yes, so my talk today will have two parts. In the first part, we look at this question of how feature geometry influences model design in the context of graph machine learning, in particular, looking at message passing graph neural networks. So as you might know, message passing graph neural networks are among the most popular architectures for graph machine learning. In general, they work really well for different learning tasks and in different domains, but they're not without challenges. And one of the particular challenges that arises are limitations in how well message passing graph neural networks can capture long-range dependencies in the data. In particular, if we have long-range dependencies in the data, we typically require deep networks. And with structured models like graph neural networks, we see instabilities if we try to train deep graph neural networks. This particular effect, as you might know, is very well characterized for graph neural networks and is known as oversmoothing. So we will discuss in a bit more detail what exactly instabilities here means. And then we will talk about how to design a message passing graph neural network that provably does not suffer from this effect, so that you can make basically as deep as you like to capture all the long-range dependencies that you need to capture in your learning task, and you will provably avoid this particular challenge. So this will be the first part of the talk. And in the second part of the talk, we will look at some more general architectures so that are not geometrically constrained. The geometric aspects here will be purely in terms of the data geometry and the geometry that's captured in the representations that the model learns. And we want to look at how this geometry evolves during training, and we'll make an analogy or find resemblances to a classical tool in differential geometry, namely discrete Ricci curvature and its associated geometric flow, the Ricci flow. And this sort of perspective will give us some insights or some hints regarding model design and the design of training protocols. Okay, so this will be the second part, but let's start with the first part of the talk. And oops. All right, great. Okay, so before we get into the details of oversmoothing, let me just remind you what message passing graph neural networks are. So message passing graph neural networks, as we said, is like one of the most popular architectures for deep learning on graphs. And each layer in the graph neural network implements this paradigm called message passing, which we can essentially write in terms of two functions, and a particular structure of those functions will determine the particular graph neural network architecture that we're using. So in general, a graph neural network learns a joint representation of two types of information that are given in our input graph, namely the adjacency. So that means the connectivity, which node is connected to which other node. And then a second kind of information that we have in attributed inputs, where we have some attributes either on the nodes of the input graph, sometimes also the edges as well. In our setting, let's consider attributed graphs that have attributes on the nodes and that have this connectivity structure. Those attributes on the nodes will be the initialization of the feature representations that the model learns. And then in each iteration of message passing, we will update those representations. The first part of this update is computing the so-called message that you see written schematically here. So what this function does is that for every given node B, it looks at the neighborhood, so the one-hop neighbors that share that are connected by an edge to our center node. And then we look at the representations of those nodes and aggregate this into a multiset. And here this aggregation can be any kind of statistical aggregation. It can be an average, it can be element-wise max. So there are different ways of implementing that particular function. But we compute some sort of statistical aggregation, and that gives us the so-called message. And then we pass our current representation and this message that we just computed into an update function. That update function is a trainable function, so you can think of something like an MLP. And the output of that is our updated representations. So this is one iteration of message passing and corresponds to one layer in the graph neural network. And then if we build a deep graph neural network, that means we stack a couple of those on top of each other. Now, what can go wrong? One challenge that might arise are these already mentioned instabilities called oversmoothing. So imagine we perform message passing. We want to update the representation of a node that's in a very densely connected area of the graph. So let's say if you see, or maybe you don't see my mouse, but let's say we pick one of those nodes here that's in a very densely connected area. Then if you think of this message function, if we are in a very densely connected area, then the nodes in that area share a lot of common neighbors, right? So this statistical aggregate, this message that we're computing, looks very similar in that whole region. So if we sort of keep doing updates with something that locally looks very, very similar across nodes, that means that any differences that we had in the original attributes is sort of being smoothed away, right? So we have a kind of representational collapse where even if the nodes initially were dissimilar, they become more similar after a few layers. So this is something that basically with this message passing scheme, we can't really avoid in densely connected regions of the graph. So one thing we might do is to say, okay, we build relatively shallow networks, so we limit the number of layers so that this kind of collapse of the representations doesn't happen. However, if we want to represent long-range dependencies, so if we have a downstream task that depends on long-range dependencies, so suppose the prediction at this node depends on some information over here, right? That has to sort of travel several iterations of message passing throughout the network. Then we need a deep network in order to be able to capture that information, right? And this is what we mean by instability. So we have this representational collapse in deep networks, and shallow networks are not rich enough to encode these long-range dependencies. So the standard, or one of the standard ways of implementing a message passing graph neural network is with graph convolutions. So here you see this sort of, if we put the message, the aggregation function and the update function together and write this as a graph operator, then you see this equation. So here A is the adjacency, X are the features, and W are trainable parameters. So those are standard graph convolutions, and this gives us one of the standard message passing graph neural networks. This is sort of well-defined for a graph domain, just to mention that here. So this function is permutation equivariant. If we apply a permutation to the features and adjacency at the input of such a layer, then this permutation affects the output in sort of the same way, right? So we have a permutation equivariant function. This represents the symmetries that we have in a graph, or that we would like to have preserved in our architecture, since graphs have permutation symmetries, right? There's no natural order relationship on the nodes. There's no sort of specific first node in the graph if we were to label them. So this gives us a well-defined message passing graph neural network. If we now do some analysis of oversmoothing, so of this effect, just to sort of illustrate how that happens here in a standard graph convolutional network, let's look at a very sort of simple task to illustrate this. So suppose our input looks something like this. So it's a ring graph. So we have n nodes, and they're connected to 2 other nodes each, forming such a ring. And suppose our downstream task is to learn distances on the graph. So we mark 2 of the nodes in the ring graph, here shown in red, and we ask the network to learn the shortest path distance between those two nodes. So how many edges do we have to traverse to get from one node to the other in the shortest way? And then what you see here on the right-hand side are essentially the training dynamics. So how these representations evolve during training. So we see a kind of dynamic equation that's, of course, very simplified here. So depending on the particular choice of aggregation and update function, this technically looks a bit more complicated, but if we sort of abstract some of the particular choices away, we kind of get this sort of dynamic equation. And then you see here in the picture this representational collapse, right? There's a unique fixed point that emerges. So we have oversmoothing. Now, in the alternative way that we propose on how to implement graph convolutions is by changing this function that we just saw for the standard graph convolutions to a unitary graph convolution. So to this kind of equation, again, A is the adjacency, X is are the features, but now we have this unitary matrix U here, right? And unitary, so this is the definition of being unitary. Notably here, this is a complex valued operator, right? So U has complex valued entries. This maybe sounds like something that introduces a lot of engineering challenges, but one can actually find good implementations of this, which you will shortly see in the experiments. So this is our redesign of the graph convolution operator. And now what does that do to the dynamics? So we apply this to the same toy example. We can have the ring graph, we want to learn distances on the ring graph. And we again look at how these dynamics evolve. And we see that instead of this collapse to the unique fixed point, we now see a very, very different pattern, right? Messages propagate as a sort of a wave-like pattern. And importantly, we don't have a unique fixed point. And then one can make this more formal, which I'm not going to be able to do in this talk. But one can characterize this oversmoothing, those emergent instabilities in terms of something that's called the Rayleigh quotient. So that's a spectral characteristic that depends on the spectrum, on the topology of the graph, and that allows us to essentially measure or quantify oversmoothing. And one can show that this Rayleigh quotient is invariant under unitary convolutions. So there's sort of, as we make the network deeper, there's not this amplification of oversmoothing and this representational collapse. So one can formally prove that unitary graph convolutions cannot suffer from oversmoothing. And in principle, we could build networks that are 100 or even more layers deep. And we would expect, and we also see in practice, that we don't suffer from those instabilities. I want to mention that this idea of unitary convolutions is not really restricted to graph convolutions. Graph convolutions are a particularly good use case because this oversmoothing phenomenon, this characterization of the instabilities is particularly well studied in the graph case. But it also happens in other architectures, in particular in other structured architectures. So if we look at group-convolutional networks, which are a very important class of equivariant neural networks, so that's used in various domains where we want to perform learning tasks under symmetries. We can show that the same kind of instabilities arise. In that context, those are sometimes called vanishing and exploding gradients, in case you have heard that term. And I just want to sort of very briefly mention here that this idea or this design of the unitary convolutions can be generalized to those group convolutional settings as well. So here you see a slightly more general version of this unitary convolution operator, and then we can plug in sort of the particular choice and recover the unitary graph convolutions. But then CNNs, for instance, which are used for image classification tasks, can also be written as an instance of group convolutions, and we can design unitary CNN architectures using this framework. And again, in principle, in those settings, we would be able to build networks as deep as we need for our task, depending on what long-range dependencies we have in a particular learning task. Let me show you some experiments to sort of illustrate that this actually works in practice. Starting again with this sort of toy example that we had previously looked at. So here on the right-hand side, you see the test laws of various graph architectures. So we're back in the graph machine learning setting here, including some architectures that were specifically designed to mitigate or to avoid oversmoothing. So of course we have the standard graph convolutions. Those are shown in brown, so vanilla GCN. And then residual GCN, so this is a graph convolutional network with residual connections that's designed to help with oversmoothing. So this is one of the mechanisms, for instance, that was proposed early to mitigate those instabilities. Also, spectral convolutions is another architecture that was proposed at some point to help with oversmoothing. We have a graph attention network, so that in each message passing layer implements a mechanism that resembles attention. And then we have the two variants of the unitary graph convolutional network. And we see here, so the dotted line is trivial performance, that most of the other architectures don't really get past trivial performance on this particular task. The graph attention network here goes a little bit below the trivial performance, but not a lot. So we can't really say that it sort of reliably learns this task. But we see that the unitary graph convolutions actually get to close to zero test error. So they're able to learn this task. And this is also something that, this is of course a toy task, but if we test this out on actual state-of-the-art benchmarks, a similar picture emerges. So in this is the so-called long-range graph benchmark. So as the name already says, this is a benchmark designed to test how well certain architectures perform in settings where long-range dependencies matter. And the kinds of tasks that you might see in this benchmark kind of roughly looks like on the schematic figure here. So we have a graph level classification task, or sometimes a regression task. So the input is a collection of graphs that might, for instance, represent the chemical structure of a molecule, and we want to predict a property. And in the table, you see in the first block different message passing architectures, including on the first row the standard vanilla graph convolutions. And in the second block, we have architectures that perform particularly well on those tasks. Some of those are variants of graph transformers. So GPS, for instance, is a graph transformer architecture. So if you look into the leaderboards for this benchmark, or at least at the time when we wrote the paper, those were the architectures that you would find at the very top. They tend to outperform message passing architectures, but one has to say they're less scalable. In particular, on the two later data sets, Kolker and Pascal, which are very large, those architectures are really hard to scale. And then at the bottom, you have the unitary graph convolutions. And you see here that in all tasks, the unitary graph convolutions made it into the top three. And they're roughly comparable in performance to these state-of-the-art architectures, including graph transformers, and substantially outperform the existing message passing architectures. I want to show one other set of experiments. So this is on a benchmark that has heterophilic graphs. So in many settings in graph machine learning, we make a so-called homophily assumption, or that the data is homophilic, meaning that the similarity structure in the features and in the adjacency is aligned. So two nodes that are connected by an edge tend to have similar features. In a heterophilic setting, this is not the case. So in particular, we might have two nodes that are connected by an edge that are completely dissimilar. So one of the data sets here, which is called Amazon, for instance, is a bipartite graph where you have buyers and sellers. And if a buyer bought something from a seller, they're connected by an edge. But of course, the buyer and the seller might have very different properties, right? So that would be an example where you have a misalignment of the similarity structure in the features and the adjacency. And that is known to present significant challenges for many existing graph architectures. Those data sets tend to be very large. So it's hard to scale those graph transformer architectures, for instance, to those settings. That's why this block is missing here. But you have at the top message passing architectures, and then at the bottom, again, the unitary graph convolutions. And you see here that in all cases, the unitary graph convolutions perform best. So those are certainly encouraging results. Before I move on to the second part, maybe I stop just 1 second for questions. Are there any questions? Yeah.
Thanks. I had a naive question on the unitary aspect of the model. Unitary over the channel dimension, or like what is the dimension that you're unitary over?
Oh, the parameters.
I guess I'm trying to think of like, is it the matrix used for like the filter kind of applied for the convolution is itself unitary, or
The sorry.
I think I'm misunderstanding how
So here, so U is the unitary part, right? And then A is the adjacency, X are the features.
Okay. Oh, so this isn't okay. So divorce myself from message passing altogether and just use the adjacency matrix. And you're fine the unitary.
So those are standard graph convolutions, right? Those implement message passing. And then we just exchange this by this operator. And then sort of in the first order approximation, you recover this again.
Okay, and so the dimensions of U, I guess is what I'm asking. So X is number of nodes, or?
So X is the feature matrix. So it's like, let's say n by D, where D are the features.
Yeah.
Is D what you mean as a channel?
Yeah.
Oh,
okay,
I
so
see.
U is D by D.
U is n by n.
N by N. Okay,
yes.
So it depends on your number of nodes.
Yes.
And so then, then how, so if those are your parameters, then how do you do this for arbitrary sized graphs? Or
so the dimension of U, it depends on on the, I mean it depends on the size of your input graph, right? So the essentially on the size of A and X, right? Which is like depends on the size of your input graph. Does that make sense? Yes.
on the feature channel, not the number.
Oh, sorry, I might have. Okay. Oh, sorry.
Super. Okay, that resolves.
Sorry, yeah. This.
Thank you.
I said it the other way.
Okay.
Thank you. Yeah,
Okay.
yeah. Thanks for resolving that. Yeah.
Any other question?
Maybe you said this and I missed it, but I mean, is there a reason that the unitary choice is needed over something like rotation matrices, something else that's invertible and norm preserving, or at least?
So invertible and norm preserving are the two important properties that we need. There is actually another. I sort of don't have time to go into details in this talk, but there's another parameterization, right? In fact, here you saw like two different versions of this. So there's another parameterization. One is complex valued and one is real valued. But sort of in this talk, I don't have the details to define
mostly
that.
asking, like, couldn't you do this with real valued matrices?
Yes, so there's
you can satisfy those two requirements.
Yes, there's a way to get a real valued parameterization. Yes.
Did you choose this? They both work, I guess. So there's
So it depends on I guess in this case, the real valued one works better. It depends on the data set. Like there's no clear winner.
Standard machine learning, probably, yeah.
I guess, yeah, if you
Multiple
like.
choice.
If you like,
Something,
yeah.
Another one, other.
Yeah.
Okay.
On some data sets, one wins, on some the
Yeah.
other, yeah. All right, great. Thank you for the questions. Okay, so for the second part of the talk, we are completely switching gears. So we're leaving graph neural networks, and we're looking at sort of more general or more standard, if you like, unconstrained architectures. And the geometric aspect that we're considering is mostly in the data geometry and in the learned features. The mathematical tools that we're using here are discrete Ricci curvature and an associated geometric flow. So I want to first spend some time introducing those tools before we go back to the deep neural network setting. Okay, so if we want to characterize data geometry, one important geometric characteristic that we could consider is curvature, right? And even if you don't have a background in differential geometry, you probably have some sort of intuitive sense of what curvature means, right? For instance, if you look at those examples up here, if we're in the Euclidean plane like this is a flat space, right? We have curvature 0, the sphere is positively curved, and then you might have seen such like saddle-like structures. This would be an example of a negatively curved manifold. This kind of notion of curvature that we have in the continuous setting, if we want to formally define that, this requires a differential structure, which in the discrete setting, so when we talk about discrete curvatures, we don't have access to a differential structure, right? So these sort of classical notions of curvature, we can't one-to-one map to settings like point clouds that we might get from a finite sample from a manifold, or graphs, hypergraphs, simplicial complexes, right? Those kind of data structures, we can't sort of build a direct one-to-one analogy to existing curvature notions. We have to use so-called curvature analogies, and I will, in a few slides, tell you one such curvature analogy and the particular discrete curvature and discrete curvature flow that we get from this argument. The kind of curvature that we're discretizing here is Ricci curvature. So this sort of intuitive sense that we just talked about, that we might have from the curvature of a manifold, this is in sort of a formal sense aligned with sectional curvature. And Ricci curvature, you can think of, if you haven't seen or haven't encountered Ricci curvature much, is a local average of sectional curvature. And from a geometric perspective, what it measures is the growth rate of the geodesic distance ball. You see here sort of the formal definitions. Since we're working in the discrete setting, we don't really sort of need to go to this continuous setting in too much detail. So let me skip straight to the discrete setting, and in particular to this curvature analogy that I was mentioning. This is a very good question that we will address in 2 slides. So bear with me. A very good question. So let's first define what we mean by discrete curvature, and then we get exactly to this question. So when we built a curvature analogy, we had said we can't define a notion in the discrete setting that is one-to-one the same as Ricci curvature in the continuous setting. So all we can hope for is to define a notion that fulfills some of the properties that we have in the continuous setting. For this particular notion that we want to use here, Olivier's curvature, the property that we are interested in is the following. So if we start 2 random walks at nearby points on a manifold, then one can show that they are likely to draw together if the manifold has locally positive Ricci curvature, and to draw apart, to diverge, if the Ricci curvature is negative. So that's a fundamental property that one can show. Why this is interesting for defining curvatures on graphs is that the behavior of random walks on graphs is something that is very well studied and that we understand well. So the analogy here in the graph setting, if we look at the picture on the right-hand side, Two nearby points could be nodes U and V that are connected by an edge. And suppose we consider a uniform random walk, one started at U and one started at V, and look at the behavior of those random walks as they proceed for, let's say, a few iterations. And if we want to look at whether they stay close by or draw apart, notice that if U and V share a lot of common neighbors, right, then it's very likely that the random walk stays close by. And if they don't have any joint neighbors, and they're sort of like star-shaped and have a lot of outgoing neighbors that sort of point away from the other node, then the random walk is likely to diverge, right? So this sort of overlap between the neighborhoods and characterizing this particular behavior of the random walks is something that we can measure in terms of an optimal transport distance between those two uniform measures on the neighborhoods, right? So this uniform random walk induces a measure on the green neighborhood and one on the blue neighborhood. And then if we measure the Wasserstein-1 distance between those two measures, this is large if there's not a lot of overlap. So there are no shortcuts that we can use for efficient transport. And it's small if there are a lot of joint neighbors, which introduces shortcuts in the transport plan. So, and then if we plug that into the proposed equation that Olivier proposes for a discrete curvature, so dg here is just the shortest path distance. If we assume for now that this is an unweighted, undirected graph, this would just be 1. And then if we have a high Wasserstein-1 distance, then we get a negative curvature, right? And this is exactly the case when the random walks are diverging. And if the Wasserstein-1 distance is small, then we get a positive curvature. And this is exactly what we would expect if the random walks stay nearby with high probability, right? So by considering this notion, we're sort of resembling or building an analogies to those properties that we have in the continuous setting. So this is one way of defining a discrete Ricci curvature. I should note that this is not the only way. There are many other proposals out there, but in this talk, we just focus on this one. Okay, now to your question. How does that actually relate to the true Ricci curvature, right? All we have here is built an analogy to one particular property, but to what extent is that actually consistent with Ricci curvature? And one setting in which we can study this are geometric graphs. So suppose we have some data manifold which is unobservable, and we draw a finite sample from that data manifold. And then we build a geometric graph in the sense that each of our points is represented by a node in that graph. And then we look at all other points that are within an epsilon distance, and we draw an edge to the respective nodes, right? And then as we vary epsilon, so as we vary the size of those neighborhoods, we get a family of graphs, which are called geometric graphs. And in the setting that we're considering here, suppose we can't observe the underlying manifold. All we have are these finite samples, and we have this family of graphs that we can construct. And we want to look at sort of the geometry of this family of graphs and what that tells us about the geometry of the underlying manifold. And in the setting of Ricci curvature, one can ask the question, if we measure the Ricci curvature, for instance, Olivier's Ricci curvature on this family of geometric graphs, does that tell us anything about the Ricci curvature of the manifold from which those points were sampled? And this would give us a kind of consistency result between Olivier's discrete Ricci curvature and the Ricci curvature of the data manifold. So those consistency considerations are sometimes called continuum limits or discrete to continuum consistency, and they have actually been studied for a few other graph characteristics. So in particular for the Laplacian and also for geodesic distances on the manifold, to what extent we can measure them on the geometric graph. What we were interested in this work are the discrete to continuum consistencies of Olivier's curvature with Ricci curvature. and we can show two types of consistencies. So the first one that you see here is a local pointwise consistency, where so this is sort of a simplified version of this bound that we get. But you already see here that we have a non-asymptotic error bound. So we can precisely say to what extent, like pointwise, we can approximate the Ricci curvature with a sample of size n, right? We do assume that it's a uniform sample, but other than that, we get a precise error bound in terms of the size of the sample. Of course, we have some dependency also on the structure of the manifold, such as the dimension, for instance. And of note, we have to carefully choose the epsilon radius, neighborhood radius. If epsilon is too small or too large, then we don't really capture the geometry well. So this parameter has to be chosen very carefully. But in the paper, we have some theory on how to actually choose this. And another consistency that we can show in this setting are consistency of global bounds. So if the Ricci curvature of the manifold is bounded below by a constant, then this property is actually inherited by the geometric graph. So in other words, by analyzing the Ricci curvature on the geometric graph, we can learn this lower bound. And this might seem like a very abstract property, but actually knowing a lower bound on the Ricci curvature of a manifold gives us a lot of information about the sort of global geometry of the manifolds. And we have some other work that I don't have time to cover today that links this, for instance, to learning complexity in training neural networks. So this is a very sort of good information to have about the data geometry and can really tell us something or also inform the model geometry that we choose and the kind of learning complexity guarantees that we get. So this was sort of a quick excursion to introduce this Ricci curvature. In differential geometry, Ricci curvature has an associated Ricci flow. Again, here we don't have to cover the continuous setting too much, but sort of for completeness, the definition of the Ricci flow in the classical sense is written here. And then Olivier, around the same time when he introduced his discrete notion, also proposed a discrete analog of that Ricci flow, where here kappa is the Olivier curvature that we had introduced earlier. And important for our discussion here is that if we consider this discrete Ricci flow on a graph, then we can show that under the discrete Ricci flow, negatively curved regions expand and positively curved regions contract. So if you look at the figure here on the bottom, let's say this would be like a geometric graph that we have built from some manifold, and then we would apply the discrete Ricci flow in that sense to it, then we would get this kind of behavior, this kind of evolution of the graph. So this is something to note for the discussion that will follow. Linking this now back to data and model geometry and deep learning. So in the following, as I already said, we want to consider sort of unconstrained neural networks. So we want to work with classical feed-forward neural networks that surely you have seen before. So here's just sort of for completeness the usual definition. And then we say that we have a linear network, or we have a nonlinear network if we have a nonlinear activation sigma. In this case here, we will only consider the case where this is a ReLU activation. And then if we don't have a nonlinear activation, then we call this a linear network. And the data geometry, so we work again in this setting where we have geometric graphs. So we have some finite sample from the data manifold. We will consider only settings where we are trying to solve binary classification tasks. So schematically, you can think of something like this. And then the geometric graph that we would build looks something like this, right? And then when we talk about feature geometry or feature representations, then we look at the sort of transformed samples that we get. So we look at those sets that, of course, depend on the finite data set that was our input data. And in the experiments that I'm going to show you, we will see some synthetic and some real data. Those are all relatively simple data sets so that we can sort of perform all of the geometric analysis and build the geometric graphs and then also compute the curvature on those in a relatively scalable fashion. So the synthetic data sets that we have are low-dimensional manifolds, where, again, we work in this binary classification setting, which is here colored in yellow and violet. And then the real data sets, we use very simple benchmark data sets. So we have MNIST, we have Fashion MNIST, and CFAR. And in each case, to make it a binary classification problem, we just take two classes. And then overall, the results that I'm showing you are based on over 20,000 trained networks. So there's some statistical power behind the empirical observations. So if you think back to a couple of slides, we had talked about this sort of evolution of the geometric graph under discrete Ricci flow. So in order to approximate this, we define like a quantity that we can sort of computationally measure, namely what we call the local Ricci evolution coefficient. So this, in order to define this, we first need some measure that tells us something about whether node neighborhoods expand or contract. And this is sort of in a discretized fashion measured by this quantity, where d here are the shortest path distances. And then the one sort of property that we had already mentioned earlier is that under this discrete Ricci flow, positively curved regions contract, negatively curved regions expand. So we would expect that the Ricci curvature, Olivier's Ricci curvature, that we measure on the geometric graph that we build from the input data and then from the transformed samples will negatively correlate with this quantity. And in order to measure that, we simply look at the Pearson correlation coefficient across layers, which is defined here. Of note is that the way we measure Olivier curvature here resembles what is in the discrete geometry literature called a scalar Olivier curvature. Right? The way we had introduced Olivier curvature earlier was at the level of an edge. But here we want to measure sort of an aggregate of curvature at a particular node, at a particular sample point. So we look at this aggregate, and this is sometimes called the scalar Olivier curvature. Okay, so if we now look into some real data, those are the real data sets that we had seen earlier. We see that this correlation coefficient that we had just defined is basically consistently with very few exceptions negative. So here you see averages and then in brackets the percentage of nodes that have this particular property, and you see that it's very consistent. So this is a global phenomena that we have this negative correlation. So this is a first empirical evidence that in fact we have sort of this evolution across layers during training that seems to resemble a Ricci flow-like behavior. And then another way of measuring this is to go back to what we know about the evolution of a graph, not necessarily a geometric graph, under the discrete Ricci flow. Namely, one setting where this behavior has already been explored, including theoretically, is the problem of community detection. So community detection means I have an input graph, and I want, in an unsupervised way, assign labels to the nodes in the graph. And those labels should be assigned according to dense subgraphs that I have in the graph. So in our setting here, let's say again, this is sort of schematically speaking, maybe our data manifold in a binary classification problem. And then if we take a finite sample, build the geometric graph, we might have here like a very slight community structure. So we have two regions in the graph that are a bit denser connected than in between. So this would be a hint of community structure. And then over here, this would be a case where we have strong community structure, right? We have two very dense graphs and then only few connections in between. So this would be an example where we have strong community structure. And one can show that if this is an input graph and we apply Ricci flow to this input graph, that I have exactly this evolution. So a kind of rewiring happens with the graph that goes from something that has sort of only latent community structure to a very strong community structure. And one can, in fact, use this also for community detection. There are algorithms for this, including this paper here that we published earlier this year, gives a theoretical analysis of this evolution and then also talks about how to actually use this for community detection. So this sort of behavior of how the graph evolves under Ricci flow, this is something that's quite well studied in the community detection literature. And now we want to apply this to those learned feature representations. And so we had said that under the Ricci flow here, the sort of community structure becomes stronger, right? So our idea here was to measure, look at measures of community structure and see how they evolve throughout the network. And two such measures that one can consider are modularity and normalized cut. Actually, both of them are also well studied in the community detection literature, and there are very well-known algorithms that build on those characteristics. We use them here to sort of measure how much community structure we have. And we see that indeed community structure emerges, so in line with this observation that we made earlier with the geometric graphs evolving as a Ricci flow. So the first sort of model design choice that we then took a look at is the role of nonlinearities. Namely, for this sort of behavior to happen, what the network basically has to do in the discrete approximation in the geometric graph is to perform this kind of rewiring. And if we first look into a linear network, so a network that does not have a nonlinearity, we can actually show that the network is not able to perform this sort of rewiring, right? So the empirical results that we saw earlier with the that were indicative of having a Ricci flow-like behavior, those were in the nonlinear setting. If we say we throw out the nonlinearity to test sort of how important nonlinearity is for that particular behavior, we can show provably that this sort of rewiring, this sort of Ricci flow-like behavior is provably not possible. If we put the nonlinearity back in, then we can show that it's possible and that the network is provably able to rewire the geometric graph in a way that resembles a Ricci flow. I think I'm already well over time, so maybe I just skip ahead to the summary to give some more time for questions. So just to summarize what we talked about. So in the first part of the talk, we talked about designing graph neural networks and also briefly mentioning more channel architectures that are capable of capturing well long-range dependencies in the data and building deep networks that provably do not suffer from instabilities that often arise in those settings. And we saw also in experimental results that in particular for graph structured inputs and for graph learning architectures, this works really well. One can both characterize this theoretically and one also sees on benchmark data strong improvements. And then in the second part of the talk, we discussed Olivier's discrete Ricci curvature on geometric graphs and discrete to continuum consistency results, and then also discussed a bit how this sort of framework, the discrete Ricci curvature and an associated geometric flow, can be used to study feature representations in deep neural networks. And we find evidence that those representations evolve in a way that resembles a discrete Ricci flow. Here are the co-authors on this work. So Bobak and Lucas did the first part of the talk on the unitary graph convolutions. Nicholas was my co-author on the discrete to continuum consistency results, and then Moritz led the work on the last part of the talk on the evolution of feature geometry that resembles a Ricci flow. All right, and my very last note, my group is hiring both PhD students and postdocs. If anybody's interested, please send me an email. Thank you.
Right, thank you. And we open the room for questions. So, if you have any.
Hi, thank you for the talk. I'm really interested in the point that you made towards the very end about how simply just applying the ReLU activation function is able to change the relative distances between the pairwise neighbors. Could you give a little bit of an intuition about how that happens, or like a proof sketch for why that is?
So a proof sketch I'm not able to do briefly here. This is please take a look at the paper, but it's a lengthy proof, unfortunately. So I tried to give sort of the statement here is very technical, even though it says informal. So this is already sort of the informal version. But yeah, the kind of intuition that I tried to give was this sort of rewiring analogy, right? So without the nonlinearity, you basically show that those learned maps are graph isomorphisms, right? So there no change in the structure of the graph happens. And then once you put the nonlinearity back in, you basically show that it's not an isomorphism anymore, and you can show that sort of this rewiring behavior is possible, right? So the sort of analogy to the Ricci flow here is built by a particular way of rewiring those graphs. Yeah, I don't know if that helps. Yeah.
Hey, thank you for the very nice talk. I just have a couple of questions about about this discrete Ricci flow. So I mean, especially the way you've drawn this picture here, I kind of got what I was saying before about how it does correspond to normal curvature in some continuum limit. But does the Ricci flow commute with that continuum limit? So you've kind of drawn in this way that this is kind of implied to be the case.
Yeah, fair point. So no, for the Ricci flow, we don't have any sort of continuum limits. So the only continuum limit that we have in the literature are really only those two. It's certainly a bit of a stretch, if you like, to then say that we can also make sort of this discrete to continuum analogy for the Ricci flow. That's a fair point. That's sort of a leap of faith that we're doing here. I'm not aware of any sort of consistency or continuum results for the flow. Yeah.
I see. Okay, so that's okay.
That would be I would say that's a great open question if somebody is looking for a problem to look at. Yeah.
For a moment, there is a question in the room. Do you want to unmute and ask?
Oh, online? Yeah.
Sorry,
Sure.
yeah.
Can you hear me?
Yes.
Well, thank you for the talk. My question is, when you wanted to construct the data graph or data manifold, so if the data is living in a high dimension, how is this compatible with the pairs of dimensionality? Like, it's like when the dimension is high, everything is equidistant, but you're using a notion of a distance.
So are you talking about the discrete to continuum consistency results? So there is I only mentioned this briefly, but so in both of those non-asymptotic bounds that I showed here on the slide, there's a dependency on the dimension, right? The intrinsic dimension. And then the ambient dimension here, so notice that we're not requiring any information about the underlying data manifold. In particular, we don't require access to the geodesic distances. So we only measure distances in the ambient Euclidean space. And there's, of course, sort of depending on the dimension of that ambient space, there is some sort of dependency here on this term, what I just called approximation error of those distances. Here, there's some sort of curse of dimensionality happening. In the paper, we characterized that in a bit more detail. I just hit that here in this one term beta. Does that answer your question?
Yeah, thank you. And another quick question. In the continuous Ricci flow, we know that there is a fixed point, with some assumptions.
Yeah.
Do we have the same thing here in the discrete case that, there is a like maybe flat or a simple or uniform curvature at the end of the flow?
Yeah, that's a great question. To my knowledge, there are no such results. I would imagine that maybe, so I don't think something like this would hold in general, but you might be able to show something for special classes of graphs. So for instance, Ricci flat graphs is for instance something that people have studied. So we know something about like what classes of graphs have those properties. So perhaps there's a setting where you can show something like this, but I'm not aware of any results. But yes, it's a good question.
Thank you.
Yeah.
Hi, I've got another question. I'll try to articulate it well enough, but it's kind of a fuzzy question.
Okay.
So again, with the Ricci flow example, I'm curious if my features have some additional structure to them, like equivariance, would you expect these types of structures to still appear? Or would kind of the smoothness of those types of structures or the fact that things should be related under certain transforms, would that interfere with any of this? It seems like you've made a this is a general result, so I'm just kind of curious how it would act in those settings.
Yeah, so this is a really interesting question, and in fact one that we have thought about to do as like sort of a future work. Yeah, I don't have a good intuition, but I think it's a very interesting question. It's something we should look at. Yeah, I would imagine it's you probably see similar behavior, but I would imagine that some interesting structure emerges.
Yeah.
That one can characterize, but how exactly that looks like and what one can show in this setting, interesting question.
Cool.
Yeah. Thanks.
I'll ask more questions about that offline.
Yeah.
Right, and one more question.
Thank you for the talk. Part 2 was really great. Very interesting result. I was wondering specifically about the community structure detection.
Yeah.
So this is useful in that case, I imagine, but this also feels like a result that would be really relevant in generative modeling, where you're trying to draw data points from a distribution. If you are able to separate out things very nicely, it feels like this would be useful. I was just wondering if you had any thoughts or like connections that you can make there.
That's not a direction I have thought about yet, how to connect this to generative modeling, but I think it's a great question and something that should be explored. So yeah, so I don't think anybody has looked into this. So I would say that's probably open. Yeah.
Any other question? Online? All right, doesn't seem so. So I think we can just thank Melanie once again for the wonderful talk. And yeah, just thank you.